for semantics and so on. So I'll start slowly. There will be a lot of somewhat technical definitions. And as I go, I will formulate. So much of what I'm going to say, I very much want to have formalized in Coq. So definitions clearly can be, all the definitions are there. Not all the proofs are currently written, because when I started to do it by hand, I just decided that it's too tedious and it's easier to wait until we have started the Coq formalization. So there will be some very clear tasks for Coq formalization. And much of my inspiration comes from Thomas Stryker's book, which I think, probably many of you have seen. It looks totally terrible when you open it, but it's really a very important foundational book. Essentially, it's the only book, as far as I know, where semantics of the calculus of constructions is presented at the level which a mathematician may consider to be rigorous enough. And so I will start with the definition of contextual category, which, for a reason which will become clear later, I don't want to call it category, some sort of a category, so I'll call it a C structure. So today's title are C structures. And I will start with the standard definition, and then I'll proceed to give an alternative definition. And proving the equivalence of the two will be one of the tasks for Coq formalization. So let me, I'll follow the notes. First of all, for those of us who have been working with univalent foundations and know the concept of H level, I distinguish two, actually, even without it, it's understandable. So I distinguish two different notions of a category. So there is something which I would just call a category, usually, and that means a category up to an equivalence. So the idea, let me just say a few words in general. The idea is that when one defines a mathematical object, one must define also what is meant by equivalence of two objects in that class. So by defining a class of categories, I have to specify what a category is as a structure. But I also have to specify what I will call, what is the notion of equivalence with respect to which all my statements have to be invariant. And so there I have two different concepts of a category. I have a category up to an equivalence, and I have a category up to an isomorphism. And yes, up to an equivalence is an abuse of language, but it's just simpler to put it this way. So in the univalent foundations, there is a very precise way of stating it, and that's just the difference between taking the type of objects of a category to be of H level 3 or of H level 2. And so a C structure is a collection of data of the following form. Sorry, I haven't used the chalk for a very long time because I have whiteboard in my office, so I lost the skill of writing eligible in chalk. So it's collection of data of the following form. First, it's a set level category. So category up to an isomorphism. And C structure, let's just call it C. A set level category, and we all know what a category is, so it's a set of objects of C. Then either it's a set of morphisms of C, or I'll just write morphisms from X to Y as usual. So that's the usual category, but it's extremely important here that it's up to an isomorphism.
So set level means objects form a set.
Set level means object form a set. It means objects form a type of H level 2.
It means we care about equality of objects rather than just isomorphism.
Yes, it means that we care about equality of objects rather than isomorphism of objects. It's not about the size.
So I don't know what caring about has to do with mathematics or definition.
Well, in set theoretical foundations, any category is set level by definition, because there is no notion of type of H level 3.
Well, doesn't it also depend on, like you were saying, how you define what sort of category you want to bring?
Yes, but that is not included into formal foundations. This need to include how you define equivalence.
I also don't know what you mean by up to isomorphism. You didn't write it, but you said up to isomorphism. I don't know what you mean when you say that.
Thank you, Dan. Here I don't mean up to an isomorphism. I just mean a set level category. What I meant when I said it is that, like, a category which is equivalent to a point category but not isomorphic to a point category will be two very, very different things for us.
For people who are not familiar with category theory, it might be worth mentioning that this is not usually the case when one works with categories.
All right. Usually, if something is equivalent to a point, then you just can think it's a point. In our case, we'll have to deal with with sizable categories which are equivalent to one point category, or to some other simple category. But for us, it will be important to have all the structure in a precise way. So a function L from OP-C to natural numbers, an object in C. As always, well, or as often, I will write something belongs to C, meaning something belongs to objects of C. A map FT, which is the abbreviation from the word father. That's how Tom Stryker called it. So from OP-C to OP-C. So this will all have to formalize in Coq, by the way. So we can one can kind of start looking at for each x in C, a morphism Px from C to Ft of C. X, excuse me. Thank you. Yes, X is in C, so in ob of C. It doesn't look pretty, and it's not going to look pretty for a long time in my lectures, but that's the best which people have managed to do, I think, in formalization of type theory. There are arguments about that, but we can discuss it later. Well, but in all of that definitions, one talks about semantics, but one doesn't give a definition of a type theory. That, as far as I know, is the only definition of A-type theory which currently exists. So now here, for every x in C such that x is not equal to the point, and for each f from y to the father of C, an object which is denoted f upper star of x I'll get there. Y is another object of C. But since I'm talking about dimorphism, I kind of think that I don't have to mention it. Kind of, Coq would figure it out. And the morphism Q fx from f upper star of x into x. Now, this strange bunch of data should satisfy the following conditions. Collection of data of the following form, satisfying the following conditions. So this function here, which assigns a number to every object of C, maybe I should call it something like length. It's length. Or maybe it's syntactic length would be better if there is some conflict, but I'll just call it length. So the only object of length 0 is the point. Yes, we'll have the square soon, and then it will be clearer. For every x such that L of x is greater than 0, or equivalently x is not equal to the point, one has L of the father of x is L of x minus 1. Father of the point equals point. I'll give another definition of what a C structure is, which maybe will make things more kind of nicer to think about. But for now, one has to deal with that. For PT is a final object, or as some prefer to call it a terminal object. Now 5, for every x such that x is not equal to the point, and every f y to the father of x one has father of f upper star of x equals y, and the square f upper star x q f x x y f ftx px p f upper star of x is Cartesian, or is a pullback square. Now, squares of this particular form, up to identity, not up to an isomorphism, will be called display squares sometimes, display squares. And these maps Px are usually called display maps, if I'm not mistaken terminology, I think. Now, there are just two conditions left. So for every x which is not equal to the point, one has identity of x upper star x equals x, and again this equals means equals, not isomorphic, and q of identity, father of x is identity on x. So in other words, this square, provided that f is identity map, this is also identity map. And the seventh condition, for all x, y, for all x such that x is not a point, for all f y to ft of z and y ft of x, and g z into y, one has q f g x equals q f x q g f upper star of x. So again, this just maps means that if one starts with this square, adds here z, then the composition of the squares is equal to the square built on the composition of functions. And again, equal here means up to equality of objects. This one? Here? That's a good point. Nothing is said. The top map is this. It's q g f upper star of x, because y is assumed to be the father of x. So this map is exactly the same kind of this map. So I can build a canonical square on G. And then I get here Q. Z. Here will be G upper star of F upper star X. And here will be Q G F upper star X. It's Q G F upper star X. No, this is just a map. This square is exactly similar to that square. So here, for every x and every map from y to the father of x, I build a square. So here, this is my x, and this is the father of that. Yeah, we have this condition here. The father f upper star of x equals y. Now, a couple of notations. Well, actually more than a couple, but So I'll write Bn of C as the set of objects of length n. Let me say, I'm not sure I'll need all of the. I'll write B of x as the set of objects y such that the father of y is x. So these are kind of objects which canonically lie over x. Now, the following very important for us notation is Bn tilde of x. So this is the following thing. This is the set of pairs.
You said X and wrote C.
I wrote C correctly for a change. Excuse me for saying X. So it's a set of pairs XS where X is from Bn and S is the map from the father of x to x, which is a section of P. So P x S equals identity. Now this will only be used for n greater than 0. This notation. And this notation is for n greater or equal to 0. So for now, let's say that is what I want to define. Now, a few words about the nature of these objects. So because it's all up to identities, this is kind of it's an algebraic theory, some sort of generalized algebraic theory. Yes, and I'm going to do it in a moment. So
Every place where it says x
not equal to something. So there is this notion of semi or quasi-algebraic theory. It's a theory which is defined by operations which are not everywhere defined, with the domain of definition of each operation being defined by equations on the preceding operations. That's actually little known to usual mathematics, but very important class of theories. On the level of classifying categories, it corresponds to Cartesian categories. And so the good thing about this quasi-algebraic theories is that one can always build free objects. Despite the fact that it would seem to be difficult because operations are not everywhere defined, there's a very simple argument which shows that one can always define a free object. And the argument goes like that. Let's ignore for a moment the size issues. Let's believe in the set of all sets just for a second. Let's take, suppose I have some sort of a sketch for such an object. Let's take all maps from this sketch to objects of my kind. Let's take the product of all these objects. There will be a lot, but we can limit their size by something. Just out of general reasoning, it's clear that the size of such a thing cannot be much bigger than the size of the original sketch. So let's take the product of all of them. And the direct product of oh, yes, and I didn't mention that they may have many types. So it's multi-sorted theory. And the product of this series is given just by the product of on each of the sorts. Yes, there will actually be n disjoint union n times n sorts. So there will be a sort for each for objects of every length, and then sort for morphisms from object of length n to objects of length m. So I'll have n disjoint union with n cross n sorts. Yes, after I did that, because if I tried to do it with just like one sort for all objects, and then one sort for the morphisms, then I would have trouble with this non-equal. But if I allow this countably many sorts, then there is no trouble. There is one other place which requires some care, because the condition that the square is Cartesian has an existential quantifier in it. There exists a unique function. But there is a lemma which says that if one has a theory which in its definition has axioms which involve there exist unique, then it can always be converted into one without existential quantifiers. So yeah, you declare that there is a map between the corresponding home sets. And so now let me finish this short explanation of how to construct free objects. So one takes all maps from the given sketch to objects of our class. One takes the product of all of these objects. And then in that product, one takes the intersection of all the sub-objects which contain the image of the sketch. So essentially, the only thing which one needs to know is that one can take a direct product of sorts, and that will correspond to the direct product of in the theory. And one can take intersection of sub-objects, and they again will be sub-objects. As soon as you have these two properties, this construction gives a free thing. This free thing can be arbitrarily complex. I mean, because of the maps where operations were not everywhere defined. When one takes a free thing, it can be very messy. And one of the things which I'll discuss in these lectures is, in the case of contextual categories, what kind of conditions on an equivalence relation one needs in order for the quotient to be well-behaved. And that's a crucial thing for the definition of reductions in type theory. What conditions the reductions should satisfy so that they don't produce some kind of blow up of the.
Can I just get a gloss on your proof? You're saying that the algebras for this thing, the forgetful functor preserves limits, because you do products and sub-algebras.
Yeah.
If the forgetful functor preserves limits, then there must be a left adjoint, which is the free one. And you're just ignoring questions of size, which you said in the beginning.
Yeah, I think that's.
If you add the size considerations, then it's the proof. You're just reproving the adjoint functor theorem, right? The existence of the free algebras.
Yeah. Thanks.
And that is one of the standard proofs. Yeah, that's
Yeah. At some point, I discovered for myself this idea of intersecting things, and I just thought it's so cool and so simple that I haven't thought about the abstract version of it. So the next thing which I need to define, and this will be a stepping stone to the next subject, is the concept. So I'll start with an almost obvious definition. Let C be a C structure. A sub-C structure in C is a subcategory in C which is closed under taking the point, taking the father, taking the canonical projection, taking Q's, taking F stars, taking Q's, and such that display squares remain pullback. Again, here it's important for it to be a subcategory in set theoretic sense, so one doesn't assume that any object isomorphic to an object is an object, which is sometimes, which I would normally assume for a category. And yeah, so one lemma about substructures is that intersection of any family of substructures is a substructure, which is what we have discussed just now. And now the first actual lemma. Let's see if I. Is it visible here from?
Yep.
Yep. So lemma let do the notations right. C prime and C2 prime be two sub C structures in C, such that for every n, Bn of C prime equals Bn of C2 prime, and B tilde n plus 1 of C prime equals B tilde n plus 1 of C2 prime. Then C prime equals C2 prime. So I required them to have the same objects, but instead of requiring them to have the same morphisms, I only required them to have the same B tilde sets. So I only require that a section of a display map which belongs to the first subcategory also belongs to the second, and vice versa. So the proof is simple, and proof. So we only need to show that the sets of maps, the sets of morphisms in these two right. We only need to show that the sets of morphisms for these two sub-objects coincide. So it's enough to show that the set of morphisms in C prime is a subset of the set of morphisms in C2 prime. So suppose I have let me just get the things right here. So suppose I have some y and x, and the morphism f going from y to x. And suppose it belongs to C prime. I want to prove that it belongs to C2 prime. So let me do this. So that will be px ft of x. This will be y. That's, I'm drawing square diagrams because of Cox, because of LaTeX. Excuse me, I probably should have been written much more simpler. So I have a commutative diagram of this form. Actually, well, this part you can ignore if you want. So this is the composition of f with px, and by induction. So I'll proceed by induction. Excuse me. I need to proceed by induction on L of x. So on the length of x. So if L of x is 0, then x is the final object, and there exists a unique map, and we assume that it belongs to the substructure. Now, suppose everything is proved for smaller, for objects of smaller length, and I have a map from a morphism from y to x. So I take its composition with the canonical projection here, take the pullback, and then because my original map was like this, I have here a section SF such that composed with this Q, it gives me back the map F. So by assumption, by induction, I know that this belongs to C2 prime. Now, because it is a contextual substructure, this belongs to C2 prime. By my assumption on tildes, this belongs to C2 prime, and their composition belongs to C2 prime. So from this simple diagram, one can see that the information about at least a substructure is fully contained in this sets Bn and tilde Bn. Now, give me just a few moments. Now we can ask the following question. Suppose I fixed some subsets in Bn of C and in B tilde n of C. What would be the conditions on these subsets which would guarantee that they come from a C substructure? And by this lemma, we know that then this C substructure will be unique. And here we have the following proposition. I'll probably erase this very beginning. So a technical definition, let's call a pair of subsets of this form saturated if they correspond to a C substructure. So proposition, a family of subsets Bn in Bn of C, Bn plus 1 tilde in Bn plus 1 tilde of C is saturated if and only if the following conditions hold. The point is in B0. If x is in Bn, then the father of x is in Bn minus 1. In Bn plus 1, let's say in Bn. Cleaner. If S from the fuzzer of x to x is in Bn plus 1 tilde, then just a second, I need to. This is something which one has to draw. So there will be x prime in B n plus 1 plus I. So let me draw this situation here. So I have x ftx. Here I have x prime such that some sort of fti of x prime equals this. And yes, and I also forgot to introduce a notation. Here is a notation. So I'll write pxi for the canonical map from x to fti of x. So px1 equals px, and px0 equals identity. And I have a map here. Excuse me, this is slightly technical. First of all, it's the other way around. Second of all, I think there is a slight mistake in what's written here, because I want. No, it's okay. So this is ftx prime. This is x prime. This is pxi. This is px prime. And then I can build px prime upper star of x. Should I have, that must have been this. And I can build px prime I upper star of x prime of here. It will be q px prime I px I. Yes, I will read it. Sorry, I didn't have a diagram in the text, so it. So here, this is a display map for x prime, the canonical map to the fuzzer. Just the single fuzzer.
You need to remove the prime from the left-hand side of the equation.
Thank you. So this is the I times iterated fuzzer, and I'm taking the pullback of this x prime along the I times iterated fuzzer of x. And then I require well, no, it's even slightly more complicated. So I also had S here and section, and then I have the pullback, because it's a pullback square. I have a pullback of the section.
That's got to do with x, not with x prime, in your original notation on the left before.
And it was right. No, it's my. Actually, I do have a diagram here. So excuse me, I will redraw it. Okay. So that's how it's supposed to be drawn. Ft of x, ft of x, fti of x prime, px prime, s px. And here there is a p star x prime ftx I minus 1 yeah, and p star of x. Wait. That was my notation, right? So the pullback of actually, I mean, my notation in the paper is like this. So maybe I should keep that. And so here, this is exactly the same thing again. Well, I think now it must be correct. I know it's tricky, but in these things, all of the theorems about all the substitution lemmas for the type theory are hidden in this one theorem. I mean, the fact that the substitution lemmas imply the syntactic category and stuff like that.
So there's a side condition that
And so here,
x prime is father to the I of x, yeah? The side
yes,
condition is
yes,
prime.
yeah. I didn't yet.
So it should be father.
So the upper left is just, this is the projection, that's its section. So that's the pullback of the section along this map. This is some kind of a Q map, and this is the pullback of S along that Q. And the requirement is that this pullback belongs to B tilde, whatever it was, n plus 1. So basically what it says here, I would like first to require that the pullback of a section belongs to my set of sections, subset of sections. Now, but the pullback with respect to what? I cannot say to any map because I still have not defined that the maps are the same. So the first thing which comes to mind is to include here the projection. Turns out not to be enough in order to ensure the validity of the proposition. So one has to include this Q from the projection. And the second, and so this is, what did I do wrong? There is one other condition, that's number 4. And then there is number 3. If S ft x to x belongs to B n plus 1 tilde, then x belongs to Bn. to be n plus 1. That's kind of easy to miss, but the idea is that if one has a section, then it's both of its ends should belong to the set of objects. So now condition number 5. There are 6 conditions total, just to and they ideally correspond to kind of 6 main things which one has to prove to show that something is a type series. So these are really really meaningful in our context. So the next thing is exactly the same. Maybe I shouldn't even draw it, but here instead of a projection there is a section. So there is an iterated there is an iterated projection here with one section on top, and the pullback of it along a section now. Now one could argue that one also would need similar axiom for the pullback of not a section but the projection itself, projection itself, but that that follows. Why does it? Just a second. That's supposed to follow. Let's figure it out. So you know what? I think there is actually that's not a very well written paper, and I think there is simply a mistake in it. I mean, it's not an important mistake. It's a mistake in the formulation of the proposition, while the proposition itself is proved in the correct way. But one actually does have to require things for the projections, I think.
When you talk about a paper, do you mean your own notes?
Yes, or not. Yeah, you're. Wait. I do mean, yes, of course, I wouldn't say that about somebody else's paper. Yeah. No, actually, I think it's true that there are only 6 conditions. Why that condition follows, why this other 2 follow from this, I'll prepare for the next time. So that was the 5th condition, and the 6th condition is that if I have x, px, ftx, x, and here then I will have px upper star of x, and here will be the diagonal of x. And then the condition is that if x is in B, then delta x is in B tilde. So the diagonal section belongs to the set of sections. Now, I will not try to provide a proof because it's a bunch of diagrams. And again, all of that we'll have to formalize in Coq, excuse me.
Proof of what?
Proof of the fact that if these conditions hold, then this pair corresponds to a well-defined contextual subcategory of C. If and only if these conditions hold. But proving it in C shouldn't be very difficult because all of that is actually algebra. I mean, this is not really category theory. It's really algebra with partially defined operations. So it's just proving a lot of algebraic equality. So I'll stop here today, but I'll say what I'll discuss the next time. I'll usually speak for an hour because I think that's more than, at least for me, it's always more than enough to kind of lose focus. And so what this proposition, what this proposition suggests is that all of the structure of this C structure is somehow contained in Bn's and B tilde n's. And what I'll do the next time, I'll write down the provisional set of, so I'll write down all the operations which one needs on this, and provisional set of axioms. And it's provisional because that's something to verify in Coq. Otherwise, it just gets too messy. So which give an alternative description of C structures in terms of these sets Bn plus Bn and B tilde n instead of as a category with an additional structure. Thank you.